Welcome, science fans, to the fascinating world of atoms. Imagine a realm far smaller than the tiniest grain of sand. Within these infinitesimal universes, electrons, those negatively charged particles, are engaged in a constant, intricate dance around the nucleus. Their movements follow a specific set of rules, a quantum choreography that determines an atom's chemical personality. This choreography is what we call electron configuration. It is the key to understanding how atoms interact, bond, and form the molecules that make up our universe. Just as the arrangement of letters determines the meaning of a word, the arrangement of electrons dictates the chemical behavior of an element and influences periodic trends. Fasten your seatbelts, fellow explorers, as we venture into the quantum realm. Get ready to unlock a deeper understanding of the elements, their configurations, and the remarkable periodic trends in chemistry. Let's begin. Imagine an atom as a bustling city. At its center lies the nucleus, the city's central core. Buzzing around the nucleus are electrons, the city's inhabitants. But these electrons aren't free to roam about randomly. They reside in specific neighborhoods called energy levels or shells. Think of these shells as concentric circles around the nucleus, each representing a different energy level. Electrons, like people, prefer to be in the lowest energy state possible, so they fill up the shells closest to the nucleus first. Electron configuration is like a census for these atomic cities. It tells us how many electrons an atom has and in which energy levels they reside. For example, the element lithium, with 3 electrons, has an electron configuration of 1s2, 2s1. Understanding electron configurations is like having a map to the atomic world. It allows us to predict how atoms will behave, how they will interact with other atoms, and ultimately, how they form the molecules that make up our world. We've learned that electrons reside in energy levels, or shells. But within each shell, there are distinct compartments known as orbitals. These orbitals represent regions of space around the nucleus where an electron is most likely to be found. Imagine them as fuzzy clouds of probability, their shapes determined by the energy of the electrons they house. Each shell can accommodate a specific number of orbitals, and each orbital can hold a maximum of 2 electrons. The first shell, closest to the nucleus, has only one type of orbital, the s orbital. The second shell has s and p orbitals. The third has sp and d orbitals, and so on. These different orbital types have unique shapes. S orbitals are spherical, like a tiny ball around the nucleus. P orbitals are dumbbell-shaped with 2 lobes on either side of the nucleus. Just as an architect carefully plans the layout of a building, the arrangement of orbitals within shells follows specific rules. Understanding the structure of shells and orbitals is crucial for comprehending how electrons are arranged within atoms. Imagine you're playing a game of Tetris, carefully fitting different shaped blocks into a grid. Building an electron configuration is somewhat similar, but instead of blocks, we're fitting electrons into orbitals, and the rules are dictated by the Aufbau principle. The Aufbau principle states that electrons first fill the lowest energy levels available. It's like filling the bottom row of a Tetris grid before moving to the next level. Electrons, being energy-efficient particles, always seek the lowest energy state, just like water flowing downhill. The order of filling orbitals follows a specific sequence: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so on. The Aufbau principle provides a roadmap for determining the electron configuration of any element, but the Aufbau principle is just one piece of the puzzle. The Pauli exclusion principle: no two alike. Imagine a grand costume party where everyone wears a unique costume. No 2 electrons in an atom can have the same set of 4 quantum numbers. These quantum numbers are like an electron's unique costume. Principal quantum number, n, indicates the electron's energy level. Azimuthal quantum number, L, determines the orbital shape. Magnetic quantum number, ML, specifies orbital orientation. Spin quantum number, MS, describes the electron's spin. No 2 electrons are identical in their quantum costumes. Hund's rule: sharing is caring. Imagine you have a choice between sleeping in a room by yourself or sharing a room with a stranger. Most people would prefer their own space, right? Electrons feel the same way. Hund's rule states that when electrons occupy orbitals of equal energy, degenerate orbitals, they first fill them singly with parallel spins before pairing up. For example, consider the nitrogen atom, N. which has 7 electrons. Its electron configuration is 122's 22p3. The 3 electrons in the 2p subshell each occupy a different p orbital with parallel spins before pairing up. Hund's rule, along with the Aufbau principle and the Pauli exclusion principle, provides a complete set of rules for predicting the electron configurations of atoms. Sodium and chlorine, a tale of 2 elements. Let's delve into the fascinating world of electron configurations by examining 2 familiar elements, sodium, Na, and chlorine, Cl. Sodium, a soft silvery white metal, is highly reactive, bursting into flames upon contact with water. Chlorine, a pale green gas, is also highly reactive, known for its pungent odor and use as a disinfectant. Their contrasting personalities stem from their distinct electron configurations. Sodium, Na. Atomic number 11, electron configuration 1s 22s 22p6 3s 1. Chlorine, Cl. Atomic number 17, electron configuration 1s 22s 22p6 3s 23p5. Notice that sodium has 1 electron in its outermost shell, 3s1, while chlorine has 7 electrons in its outermost shell, 3s 23p5. Sodium readily donates its valence electron to chlorine, forming positively charged sodium ions, Na+, and negatively charged chloride ions, Cl. The electrostatic attraction between these oppositely charged ions results in the formation of an ionic bond, creating sodium chloride, NaCl, commonly known as table salt. The contrasting personalities of sodium and chlorine highlight the profound influence of electron configurations on chemical behavior. By understanding these configurations, we can predict how elements will interact and form the vast array of compounds that make up our world. Decoding the periodic table trends and patterns. The periodic table is a meticulously organized chart revealing profound patterns in element properties. These patterns, known as periodic trends, stem from repeating electron configurations. One fundamental trend is atomic radius, the size of an atom. As we move down a group, atomic radius increases. Conversely, across a period, atomic radius decreases. This is due to the increasing positive charge of the nucleus. Atomic radius and ionization energy clues from configurations. Let's revisit our friends, sodium and chlorine, to see how their electron configurations provide clues about their atomic radii and ionization energies. Sodium, with its single valence electron in the 3s orbital, has a larger atomic radius than chlorine. This is because sodium's valence electron is farther from the nucleus in a higher energy level than chlorine's valence electron, experiencing weaker attraction and resulting in a larger atomic size. On the other hand, chlorine, with its 7 valence electrons, has a higher ionization energy than sodium. This is because chlorine's valence electrons are more strongly attracted to its nucleus due to the higher effective nuclear charge, making it more difficult to remove an electron. By analyzing electron configurations, we gain insights into the size, reactivity, and bonding behavior of different elements. Electron configurations, the key to chemical reactions. Electron configurations are not just theoretical concepts confined to textbooks. They hold the key to understanding the vast and intricate world of chemical reactions. Chemical reactions involve the breaking and forming of chemical bonds, which are driven by the interactions between electrons in the outermost shells of atoms. Electron configurations provide a roadmap for predicting how atoms will interact and what types of bonds they will form. Metals like sodium tend to lose electrons to form positively charged cations, while nonmetals like chlorine tend to gain electrons to form negatively charged anions. These oppositely charged ions attract each other, forming ionic bonds. Understanding electron configurations allows us to predict the types of bonds that will form between atoms, the properties of the resulting compounds, and the energy changes associated with chemical reactions. Unlocking the secrets, your journey continues. As we conclude our exploration into the captivating world of electron configurations, remember that this is just the beginning. We've unraveled the fundamental principles governing the arrangement of electrons within atoms, explored the periodic trends arising from these configurations, and discovered how these tiny particles hold the key to understanding chemical reactions and the properties of matter. But there's still so much more to discover. Dive deeper into the quantum mechanical model of the atom Explore the nuances of electron configurations for transition metals and lanthanides, and investigate the fascinating world of spectroscopy, which allows us to probe the electronic structure of atoms and molecules. Partly, more of this will be uncovered and delved with in physical chemistry. Embrace your curiosity, never stop questioning, and continue to explore the wonders of the universe, big and small. Thank you for joining me on this cosmic adventure. If you enjoyed this journey into the heart of matter, please like, share, and subscribe to Sleepy Plans for more explorations into the wonders of science. This helps improve the quality of the videos, and this helps promote your support for future videos. As always, have a nice night, and good night. Until next time, keep those neurons firing and never stop exploring.